was this. So we're given this. We're given that the integral from 0 to infinity of g of x times e to the negative x squared dx is equal to 6. And we're also given that g of x is odd. Okay. And then we're asked to find the integral from negative infinity to infinity of g of 2x e to the negative 4x squared dx. And I find these questions a little confusing. Like, I'm not going to lie, they're a little challenging. But typically, if we don't know what g is, which we don't, maybe we know it's odd, but okay. But if you don't know what a function is, and they're kind of asking you to do something with that function evaluated at some other place with an integral, it's almost always a good sign that we're going to do a U-substitution, and that's going to be our U. Like 9 times out of 10. If you see something like this where you don't know what that function is, and they're asking you something with that function with something else inside the function, the thing inside the function is probably going to be a U for a U-substitution. So let's try that. And I'm going to, for the moment, I'm going to ignore limits of integration. I really, really, really don't think it's a good idea when the limits of integration are infinities to try and change them to other things. I just find that there are challenges there that mean it's easy to make mistakes and you don't even realize you've made a mistake. So my preferred method of doing this is do the indefinite integral, get it in terms of u, do it, change it back to x, and then we'll see. Or maybe not. We might not even change it back to x. We'll see what happens. So I'm going to write this as well. So u is 2x, du is 2dx. So 1/2 du is equal to dx. And importantly, if u is equal to 2x, u squared is equal to 2x squared, which is 4x squared, which is exactly almost what we have here. So this is equal to the integral of g of u, that's a u, believe it or not, e to the negative u, and then dx becomes 1/2 du. Sorry. Wow, I'm really doing this well. Dx becomes 1/2 du. Okay. Oh, sorry. That's not just u, right? It's u squared. Okay, but look, this thing here is this here. I mean, without those limits of integration, right? G of u e to the negative u squared is the same as g of x e to the negative x squared. I've just got a different variable. So I guess I know I said a thing, which is I don't usually like to do the limits of integration if they're infinity and change them with the U-substitution. I'm going to do it here because I don't really see another choice, right? I have to have these to see what it's equal to. So I am going to write this as, so this is negative infinity to infinity. And here's the thing. Here it's not too terrible because u is just twice x. So if x is infinity, u is going to be twice infinity, which is still infinity. And if x is negative infinity, u is going to be twice negative infinity, which is still negative infinity. And now we can break this up. I don't know that, I personally don't see how knowing that g of x is odd is particularly, oh, I take it back. I see it now. Yeah. Sure. So because g of x is odd, yeah, oh man, maybe sorry, I feel like this should be done this way. I could be wrong though. So you could do it this way. It's perfectly fine to do it this way. But I'm thinking now that I look at this a little bit more, you could use the fact that g of x is odd. So sorry. So while this is fine, it will totally work, I think there's a better way. And the better way would actually just be to say, instead of doing this, we can actually show that this whole thing is odd. Let's call it, I don't know, let's call it f of x for a second. Is g of 2x e to the negative 4x squared. To show something's odd, you have to show that f of negative x equals negative f of x. Okay, so f of negative x is going to be g of 2 times negative x is negative 2x e to the negative 4 times negative x squared. Okay, but g itself is an odd function. So g of negative 2x, that's equal to negative g of 2x. Then look what happens. We get negative g of 2x times e to the negative 4 times negative x quantity squared is just x squared. So look at this. This is the negative of the function we started with. This is negative f of x, which means this function is an odd function. Which means since we're going from negative infinity to infinity, and I have to say, because we know that this is already convergent, then we can say this is equal to 0. So yeah, that's a little funky. Yeah. A better way to say this is that if you have an odd function, g of x or g of 2x, times an even function, which e to the negative 4x squared is an even function, an odd function times an even function is still an odd function, which is kind of neat. Yeah. Yeah.
What's the first function used for?
Which function?
Like the very first one, you want that equals 6. Like, what was that for?
They tell us this. So here's what you need. Here's what I think you need this for. And again, there's a couple ways you could go here. Personally, you need to know this is equal to not infinity, so that you know that this is convergent. So that then, right? Because I know she didn't say this in class, but to be able to say that the integral from negative infinity to infinity of an odd function equals 0, that's only true if it actually converges. There are integrals from negative infinity to infinity of odd functions that diverge. And we talked about that briefly a while ago. I don't want you to get too hung up on it though, because it's not going to come up. But that's why we need this. The other reason you might need this is if you were doing it the way I was doing it before, you could break it up into 2 integrals and show that one integral was equal to like 6 or maybe half of 6. And so the other integral is negative of that, so they cancel each other out. That would also work. So let me actually find out. So if we were doing it the other way, where we had the integral from negative infinity to infinity of g of u e to the negative u squared du, right? We had that, except we had a 1/2. And then I could break this up as 1/2 the integral from negative infinity to 0 of g of u e to the negative u squared du plus 1/2 the integral from 0 to infinity of g of u e to the negative u squared du. This is 6. And this, well, you could do another U-substitution. You could let w equal negative u, which is annoying, or and basically change this to be the integral from 0 to infinity of g of negative w e to the negative w squared negative dw. And then it ends up being negative 1/2 of 6. This is not the way I would do it. This is how I'm I'm not being super in depth about it. But yeah, so you do need that fact though to know that it converges. Okay, let's look at one other one that someone else asked me that's kind of in the same vein because it is worth talking about. Yeah. So another problem that's kind of similar. And so I definitely did write something up on Canvas about this in the discussion post. So if you want to look at it later on your own, you can go look in Canvas. The question that was given was the integral from negative infinity to infinity of 1 over x squared plus 1 dx is equal to pi, which is true. We could show it. But they're asking us to find the integral from negative infinity to infinity of 1 over, what have I got here? X squared plus 9. And it even says to do a U-substitution. So here's and I'm pretty sure this is in your table of integrals, like 1 over x squared plus a squared. But here's the idea. If you're trying to integrate something like this, you want it to look like 1 over something squared plus 1. But we have plus 9. So what we're going to do, and again, I'm going to just forget about those limits of integration for a second. I'm going to say that this is equal to, and this is where I think the tricky part kind of happens. I'm going to factor out a 9 from the bottom. So I've got 9 times x squared over 9 plus 1. The 1 over 9 can come out in front. So it's 1 over 9 integral of 1 over now what I want to do is I'm going to write x squared over 9 as x over 3 quantity squared. And now it looks like 1 over something squared plus 1. But I want this to be like a variable, not a variable divided by 3. So I'm going to do a U-substitution. I'm going to let u equal x over 3. Then du is going to be 1/3 dx, and 3 du is going to be dx. So I can rewrite this integral as 1/9 the integral of 1 over u squared plus 1 3 du, which becomes 3 over 9, so 1/3 the integral of 1 over u squared plus 1. Now, I want to show you two different things. Thing one, this is where you want to get to finish this problem, right? So if we're actually doing, right, the integral from negative infinity to infinity, and we get to here, well, again, if x is infinity, 1/3 of infinity is still infinity. And if x is negative infinity, 1/3 of negative infinity is still infinity. So this would get us to, I'm going to go this way, 1/3 of the integral from negative infinity to infinity of 1 over u squared plus 1 du. But then look, this part here in green, that has to be equal to pi. That integral and that integral are literally the same thing. They're just using a different letter. So this is going to be 1/3 of pi. And that's how you do a problem like that. I do want to say a little bit more though, because it seems like it's something that's probably worth knowing. We know the integral of 1 over u squared plus 1 is the arctangent of u. This is going to be 1/3 the arctangent of u plus c, which is 1/3 the arctangent of, I plug back in what u is equal to, x over 3 plus c. So there's a general formula for this, and it's definitely in the book. If you integrate 1 over x squared plus a squared dx, the integral is 1 over a times the arctangent of x over a plus c. Sorry if you can't read that. It looks pretty small when I'm looking on the board there. That is the 1 over a. Let me write that again. Try a little bit bigger. 1 over a arc tangent of x over a plus c. So that's how you integrate something like that. Again, these problems are not actually asking you to really do the integral. They're saying, here's what the integral is equal to. Make this other thing look like that so you can say that it's equal to some multiple of it. That's kind of the gist there. All right. Gosh, time is just flying by. Okay. So I want to just talk about stability for a moment, and then we'll jump into some more differential equations. So let's say that I have, let's do like 2 stability problems. So let's say I have the differential equation dn dt equals 2n times 1 minus n over 1,000. Now let's make it 6 minus n over 1,000. So 2 things we're going to, maybe 2 or 3 things we're going to ask. We're going to find what are the equilibria, and are they stable or unstable? Okay, so the equilibria are just the things that make the derivative equal to 0, right? Because if the derivative is 0, the system isn't changing, right? If the rate of change of n, the population, is 0, that means the population isn't changing, which means we are stable. Or sorry, we're in equilibrium. Maybe not stable equilibrium. So we're basically just trying to find where is the derivative equal to 0. So we're going to set the thing that the derivative is equal to 0. So that means we're going to go with 2n times 6 minus n over 1,000 equal to 0. So either that's going to be 0, so we're going to get n equal to 0, or that's going to be 0, which means 6 minus n over 1,000 equals 0. I think n is going to be 6,000. 6 equals n over 1,000. N equals 6,000. So those are our 2 points of equilibrium. We don't know if they're stable or unstable yet. It definitely seems like Karana prefers you guys use the phase plot method. I don't think she's talked about really the derivative method, which is fine. We'll talk about it if we need to, when we need to. So let's draw the phase plot of this, which is, again, when you're drawing this, you are graphing on the horizontal axis, the variable n, and on the vertical axis, dn dt, which we often call g of n. Even though we know that n is a function of time, we are thinking of this is really kind of independent time. We say, okay, if your independent variable is n and your dependent variable is the derivative, what's our graph look like? Well, okay. So basically my n is my x variable. So these are the values of n that make the function equal to 0. So these are going to be my x-intercepts. So the x-intercept is 0 and x-intercept is 6,000. And then I just need to know if the graph is above or below the horizontal axis. So you can literally pick anything between 0 and 6,000, like 1, and plug it in. Plug in 1, you get 2 times 6 minus a small number. So 2 times 6 is about 2. It's positive. So it's going to be positive in between 0 and 6,000 and negative on the outsides. All right. So this is where you have to, so here's what you should really get used to seeing. If the graph is going, so reading from left to right, if the graph goes negative to positive, it's unstable. If the graph goes positive to negative, stable. And here's why. If the graph is negative, that means the y values are negative. But the y values are the derivative values, meaning if the derivative values are negative, the function itself, so if the derivative n is negative, that means n is changing in a negative way. It means n is getting smaller. But n is on the horizontal axis. So over here, where dn dt is negative, n is getting smaller. Over here, right, looking at this part of the graph, where dn dt is definitely positive, n is increasing. And then over here, where dn dt is negative again, n is decreasing, so n is getting smaller. So 0 is unstable because if you're a little bit off of it, you're going to get pushed away from it, right? If you're less than 0, you're going to keep getting smaller, smaller, smaller. If you're bigger than 0, you're going to get bigger and bigger and bigger. So 0 is unstable, which is pretty typical for like population dynamics, right? A population of 0 is unstable. If you have a little bit more than 0, it's going to keep being more and more and more. So 0 is unstable. Whereas n equals 6,000 is stable, right? Because if we're a little bit less than 6,000 or a little bit more than 6,000, we're going to get pushed back towards 6,000. So whenever you're looking at these phase plots, if you're going left to right, if you go negative to positive, it's unstable. If you go positive to negative, it's stable. Left to right. Okay. I think I'll just do the one example back because I feel like we should definitely talk about these differential equations. These, as she calls them, integrating. I think she said integrating factor differential equations. They're also often referred to as first order linear differential equations. Ooh, actually, there's one other thing I want to say about something else real quick, but it's not that big a deal. Someone asked me about this, which I thought was a really good question. I'm going to change it just slightly. So someone was asking about the absolute values. Like, so let's say we solve the differential equation. So we have some differential equation. I don't really care what it is, but we're solving it. And we get down to the point where our solution is the absolute value of y equal to k times x squared. And I know I've said this a few times. It's totally cool. Oh, and also we have an initial condition of y of 0 equal to -6. And so here's what I've said. It's totally cool just to drop the absolute value. But let me show you why, because I feel like people have had questions about this and people want to know. So here's why we can drop the absolute value. I'm not going to drop the absolute value. I'm just going to solve this. So plugging in 0 for x and -6 for y, you get the absolute value of -6 equal to, 0 is a bad choice. Sorry, 0 is going to make this funky. Let's say y of 1. 0 actually wouldn't work, right? 0 would be 0 equals 6, which is a problem. So let's say y of 1 equals -6. So y is -6 and x is 1. So k times 1 squared. Absolute value of -6 is 6. So 6 is equal to k. So here's my solution. We've got the absolute value of y equals 6 times x squared. All right, but now here's the thing. Y is supposed to be a function of x. So if the absolute value of y is equal to 6x squared, it means either y is equal to 6x squared or y is equal to -6x squared, right? Because the absolute value of 6x squared will be 6x squared. The absolute value of -6x squared will be 6x squared. And it can only be one of them. It can't be both because it has to be a function, right? You can't be plugging in x equal to 2 and getting -6 times 4 and +6 times 4. So which one is it? Well, it depends on the initial condition. And the initial condition says that y of 1 has to equal -6. So it has to be that one. Now, here's the story. We could have avoided all this by just saying, I'm going to ignore the absolute values, say y equals kx squared, plug in 1 for x and -6 for y, and then you get k equal to -6, which gives us y equal to -6x squared. So I really, really, really want to impress on all of you, because it's definitely something that was challenging for me for a long time to really wrap my head around. It's perfectly safe to drop the absolute values and just to say it's going to get taken care of by the constant out in front here. That constant will adjust. It'll be negative if it needs to be negative. It'll be positive if it needs to be positive. You don't have to worry about whether or not it's going to work out. So take my word for it. Drop the absolute values. It'll be much easier. All right. So let's talk about some integrating factor problems, which I think Karan did a very, very, very good job of explaining. But we should definitely do some practice, because it does take practice to get a hang of. Do I actually have any? Of course, I don't actually have any examples. Let me just grab some here. I know I have plenty of examples right here. Not you. Yes, you. Okay. So let's look at this one. And I will try to use the notation that she used, because why not? That seems sensible. So yeah. So integrating factor. Also known as first order linear differential equations. They're called first order linear because they are first order, meaning you only have the first derivative as your highest power derivative, your highest derivative, and they're linear, meaning that they are linear in the function variable. Let me say that in less terrible. So let's say we have this equation: y prime equal, y prime plus, plus 3y equal to fine if I change that. It's going to be kind of terrible. That's all right. Equal to x. So it's a first order linear because you only have the first derivative, and it's linear because you only have y to the first power. You don't have any other higher powers of y, or whatever your top variable is in your derivative. And again, we could usually, I forget how she was doing it. Yeah, she was usually writing this as dy dx, which is fine. Either way is okay. And I will fully admit, I'm used to taking a bit of a shortcut here, but I also saw that she really doesn't want you guys to do that. So we're going to do it the long way. So yeah, in fact, let me make sure I've got it written out here so that I don't skip a step. So the first thing you have to make sure of before anything else is to make sure that you have it in the right form, meaning it has to be the derivative plus function of x. So there's your function of x times just y equal to some other function of x. People usually call this q of x. I feel like she called it g of x. Either way. And so then, yeah, we're going to multiply the whole thing by the integrating factor. She used capital I. A lot of other people use a lowercase mu. So if you see that somewhere else, just be aware that that's what they mean. So I will use I of x like her, but lots of other textbooks use lowercase mu, which looks like the letter U, but with a little extra tail on the left. So be aware, that's another thing. So we're multiplying everything by I, which is totally allowed. So I of x times dy dx plus 3 times I of x times y equals x times I of x. All right, so this is where things get interesting. You have to remember that this whole thing is supposed to be This pen is not doing it for me. Sorry. This pen is just. Here's a better pen. Sorry. This whole thing here, this is supposed to be the derivative of I of x times y. Product rule, right? It's I of x times y prime, right? So the derivative of this times this plus y times the derivative of I of x. So what we're really saying here is in this second part here, whatever isn't y is supposed to be I prime. And that's how we're going to find the integrating factor, is by recognizing that, oh, this here, whatever's multiplying by y, that is your I prime of x, or your di dx. So we're going to solve for that over here. So this, actually, that's right. This is my first step. This is my second step. So then my third step, I'm going to solve for this. I'm going to say that I prime of x, or di dx, is equal to 3 times I. Now here's what's always going to happen. You're always going to have something times I. And you're always going to divide the I over to this side. So you're always going to have di over I on the left. The left side of this will always, always, always be that. There is no other option. The right side will be whatever your function of x is. In this case, it's 3 times dx. Then we're going to integrate both sides. Integral of di over I is always going to be the natural log of I. It's really the natural log of the absolute value of I, but she's totally correct in saying that you should not pay attention to the absolute values here because we're just trying to find something that works, and we're going to pick the easiest thing. So we're going to say the natural log of I equals the integral of 3 is 3x. And yes, we don't write the plus c for the same reason. We're trying to find the easiest thing that works. So exponentiating both sides, e to the natural log of I, which is just I, is equal to e to the 3x. So our integrating factor here, I of x, is equal to e to the 3x. So that's what we're multiplying both sides by. Now I'm going to show, I think I'm going to show a little extra work here, actually, just so everyone can really see what's happening. Yeah, let me go to the other. Yeah, we have enough room here. So here's what we're really saying. We're really saying that e to the 3x times dy dx plus 3e to the 3x times y equals x times e to the 3x. That's what we've multiplied both sides by the integrating factor. Now, the left side here, in fact, let me write this on the other side so we can see it again. Yeah. So we have e to the 3x times dy dx plus 3e to the 3x times y equals x times e to the 3x. Okay, this whole side here is the derivative of the product e to the 3x times y. Let's just check mentally real quick. The derivative of this product, well, so it's going to be the derivative of y times e to the 3x plus, now we switch it, we leave y alone, times the derivative of e to the 3x is e to the 3x times 3, which is totally that. So our process is always to end up getting something that looks like the derivative of a product on the left-hand side. So then we've got this. So if the derivative of this is equal to that, then we can say that e to the 3x times y is equal to the antiderivative of x e to the 3x. right? If the derivative of something equals something, the antiderivative of that something is equal to the other something. I want to make sure everyone's very okay with this. It's kind of the key step. Okay. Chime in if you have things. Also, before I forget, let me just do one quick thing. One thing I do want to say about that is that now we have to integrate the right-hand side. And it's something that's a little bit, right, it's an integration by parts. So we can do it real quick. Let's just do it like this. So we've got e to the 3x times y is equal to, so integration by parts here. U is x, dv is e to the 3x, du is dx, v is 1/3 e to the 3x. So you've got, let's see, this is going to equal u times v. So x times 1/3 e to the 3x minus the integral of v du, which is 1/3 e to the 3x dx. So we get e to the 3x times y equal to 1/3 x e to the 3x minus, so the integral of 1/3 e to the 3x is going to be 1/3 e to the 3x divided by another 3. So 1/9 e to the 3x plus c. And now we divide everything by e to the 3x. And check this out. We're going to get y equal to, so if you divide this by e to the 3x, it cancels. And you get 1/3 x. If you divide this by e to the 3x, you get just 1/9 or minus 1/9. And so it's really, really important that you divide this c by e to the 3x. Otherwise, your answer looks kind of just bland. I mean, really wrong, to be honest, but oops, that's good. Yeah. So our answer is 1/3 x minus 1/9 plus c divided by e to the 3x. Interesting. I don't want to check it. You could check it. It is correct. But that's the process. Let's do at least another one. Let me see if I can grab one here that looks maybe a little less terrible. Sure, we can do this one. Yeah. So let's try this one. I really want to stress, she wants you to do this process. I'm probably doing a few more steps than you might want to do. So I'll try and do this next one, showing exactly the steps I feel like she expects you to kind of do. So here's the differential equation. T times y prime minus 4y equals t to the 6 e to the t squared. And just a reminder here, y prime should be rewritten as dy dt, right? Because that is, right, y is the dependent variable and t obviously is the other variable, the independent variable. So let's go ahead and just do that first. Okay. For this to be a first order linear or an integrating factor problem, you have to be able to write it as y prime plus y times your function of your independent variable, which is t in this case, equal to your other some other function of your independent variable. So you have to be able to write it as y prime plus y times t things equal to t things. I don't have that yet. I have this t here, which is a problem. So I need to divide everything by t. So divide by t to get dy dt. I'm going to write this as minus 4 over t times y equal to, divide this by t and you get t to the 5th e to the t squared. Okay, now, I guess this is less important here. So I was always the kind of person that was just like, I'm going to find the integrating factor by doing the formula she talked about, where the integrating factor is e to the integral of p of t. but fine. So let's multiply everything by the integrating factor, I of t. So I'm going to have, I want to kind of write this in a, yeah, I guess I'll write that. So I'm going to say I've got dy dt times I of t. And I'm going to write this in the following way. Plus, because I know I'm trying to make it look like a product rule. And the product rule is always, right, the derivative of one thing times the other thing plus the first thing times the derivative of the other thing. So I'm going to write this as y times negative 4 over t times I of t equal to t to the fifth e to the t squared times I of t. Okay. So let me just point out, this is a product rule. It's y prime times I plus y times I prime. So whatever is multiplying by y here, this is your di dt. Every single time. Di dt is always whatever the function multiplied by y is times I. So let's go to the other side to figure out what that is. So I'm going to have the di dt equals negative 4 over t times I. So really, 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 it's super important, right? If you've got a minus sign here, you need to make it a plus and capture that minus with your separable differential equation for the integrating factor. So here's what we've got. We've got di dt equal to negative 4 over t times I of t, or negative 4 over t I. Right? We don't need the I of t when we're solving the differential equation. Bring the i's to the left. Bring the t's to the right. So you've got di over I equals negative 4 over t dt. Integrate both sides. Natural log of I. Right? We're ignoring the absolute value that would be there. And this is going to be negative 4 natural log of t. We're ignoring the plus c as well. So she solved something like this in class really fast and got like x squared. Let me just show you the extra kind of steps. Everyone's cool. First, before exponentiating both sides, I'm going to bring this negative 4 up as a power. So that's going to be the natural log of I equals the natural log of t to the negative 4th. And then you could just say, well, if the natural log of a thing equals the natural log of another thing, the things have to equal each other. So I equals t to the negative 4th. Or you could say e to the natural log of I equals e to the natural log of t to the negative 4th. And then say I equals t to the negative 4th. Whatever floats your boat. So I equals t to the negative 4th. So I feel like the next step she wants you to take in this process, in fact, I wrote it down. Yeah. So she basically wants you to go from this. Oh, wow. Yeah. I feel like that's a big leap. Yeah. Let's go. So right. So I guess what I'm saying is I'm going to take an intermediate step. So this is equal. This is going to be. I'm going to write this as the derivative of. Right. This is. Right, that's what that is. It's the derivative of y times I. It's y prime times I plus y times I prime. Derivative of y times I. Equals, let's actually fill in what I of t is over here. So I of t was t to the negative 4th. So that's going to be t to the 5th times e to the t squared times t to the negative 4th. We should definitely simplify that. T to the 5th times t to the negative 4th is just t. And now we're supposed to integrate both sides. The integral of the derivative is just the thing that you have. So integrate integrate. So integrate, and you get y times I of t equals the integral of t e to the t squared. I suppose I could plug in what I of t is at this point. I of t over here is t to the negative fourth. So I'm out of room. Let's go to the other side. So we've got this. Y times t to the negative fourth equals the integral of t e to the t squared dt. Right? Right. Okay, to do this integral on the right hand side, well, I suppose we could write our answer at this point in that we can multiply both sides by t to the fourth and say that y is equal to t to the fourth times the integral of t e to the t squared dt. We're not done because we still have to integrate, but I want you to be extra careful here. The mistake I used to make all the time, which feels really dumb now that I know how to do it, but I used to be like, oh, you can just multiply the t to the fourth inside. That's not true. You cannot do that. You have to integrate before you multiply by the variable thing. So we have to integrate this. To integrate this, we need to use U-Substitution. So let's do that real quick over here, and then we will call it a day because it's 2:59. So to integrate t e to the t squared, we're going to let u equal t squared. Du dt is equal to 2t, so du is 2t dt. 1/2 du equals t dt. There's my t dt. So this becomes 1/2 the integral of du, and then e to the u. Integral of e to the u is e to the u, so you get 1/2 e to the u, which is 1/2 e to the t squared. So that's what our integral is. So our answer is y equal to t to the fourth times this. Well, I need the plus c though. So t to the fourth times 1/2 e to the t squared plus c. I usually like to multiply it out. I can't really say that there's a good reason. I will say for the previous problem, there was a good reason because multiplying it out, you saw a bunch of stuff cancel. Here, most people will probably leave it like this, but you could also write it as t to the fourth e to the t squared over 2 plus c times t to the fourth.